Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. We started at the end of the previous lecture to talk about this problem, which is learning with imbalanced data. Okay, so what is that problem exactly? Do you remember? What was the problem? Yeah, so we have very few positive examples. The distribution have very few positive examples and much more negative examples. Okay, and you remember the example last time of the suspicious transactions. Said that like median transactions, maybe 5 of them will be suspicious. So the distribution is very skewed, very imbalanced. Okay. So what should we do that? Or first we said why this is a problem. We said that this is a problem because most or many learning algorithms are optimized for minimizing the error. So if that's the case, then they would say negative all the time, and we will get very good accuracy, but that's not what we want. So we'll have to find a way to solve this problem. Don't remember if you saw this or not, but you saw it before at least. This is the definition of the binary classification problem. So we are still working within the binary classification framework. We assume that we have two classes, but the distribution is imbalanced. So here, this is the definition, the general definition of the binary classification problem. We have the unknown distribution. Each example from that distribution has a label of either negative or positive, and we sample the training set from that distribution, and we want to minimize the error. Okay, so error here happens when the predicted label using the function that is trained is not equal to the actual label. Okay, so you saw this probably before. And this is done on the original distribution of the data. I mean the sample that we have. Now, this is not, this is the general binary classification problem, but when we have imbalanced data or imbalanced distribution, we would like to treat the classes differently. Okay, so if I made an error on a positive example, in the previous slide, it was counted as the negative example, right? So any error, whether on a positive example or in a negative example, it is treated equally here, right? But if I have an imbalanced distribution like 1 to 9, I have 10% of the data positive and 90% of the data negative. So the error that the model will have on any positive example should be weighted differently, right? Actually, it should be weighted 9 times. In this case, more than the negative, an error on a negative example, right? Because the positive example is rare. So I would like the model, when it is trained, to be penalized more when it made a mistake on the rare class. If I penalize it more, then it will learn not to make mistakes on the positive class. It will learn better not to make mistakes on the positive class because it will be penalized more. Okay? So how can we do that in terms of the definition of the problem? You saw here, you saw in the previous slide, we have an error. That's the definition of an error, right? We didn't say whether this error is on the positive class or in the negative class. Now here, if you look at it, you will see that this same error is multiplied by alpha times y equals 1. First, what is alpha? Alpha is the factor of how many negative examples we have more than the positive example. Actually, alpha is the size of the negative set over the size of the positive set. So if I have 90% versus 10%, then alpha is 90 over 10, which is 9. Okay, so alpha is always more than 1 because we assume that the negative class is much larger than the positive class. So alpha is how many more negative examples we see in the distribution. Right. Let's say that alpha is 9. Okay, so every mistake or every error the model will do will have or will make on a positive example should be penalized 9 times more the error on the negative example. Okay. Right. What do you mean by penalize?
No, like what is the meaning?
Yes, I understand. The word itself? Oh, you don't know in English يعني ولا in this context? Okay, sorry. I thought that you know. Penalize mean punish. Okay, it will be punished 9 times more than the negative example. But I thought that your question is how? Okay. Okay, it's coming. كويس. Okay. You have a trust in me now that it will be coming. كويس, good. Thank you. I will inshallah talk about this. Yes, of course. So you see here that this is the error expression, right? When the predicted label is not equal to the actual label. Okay? Now you will see that this is either 0 or 1. And if it's an error, it will be 1. If not, then it will be 0. So this is now multiplied by alpha, which is the penalty factor, how much we will punish more or penalize more the positive example, which is based on the distribution. We said 1 to 9, then alpha will be 9. So it will be the error when it happens on the positive class, we want to multiply it by 9. But if it happened on the negative class, we will just multiply it by 1. How is that happening here? This is alpha to the power y equals 1. So if y equals 1, which is the positive class, then this will be alpha to the power 1. So we will multiply by alpha. This is in the error function. So this is how the error will be computed. Okay? So if the error is in the positive class, then we will be multiplied by alpha. If the error is a negative class, so y is 0, it's not 1, then this is alpha to the power 0, which is 1. So we either multiply by 9 in case this error happened when y is 1, which is positive, or multiply by 1 if the error happened to a negative example. In this case, y equals 0, so this would be just 1. So this is just an elegant way or nice way to combine both. Okay? Right. Now to the question on how we will penalize. Actually, first at the level of an error function, if you compare this with the error function from the general binary classification, you will see the difference, right? Now the error here is equal across all examples. Here, no. Whenever we have an error on a positive example, it will be multiplied by a bigger number, right? Which is alpha. That's at the level of the error function. We will talk about how this is implemented in reality. Okay? So if this is the error function that the model will try to minimize, then of course this is pushing the model not to make mistakes on the positive class much more than the negative class. Okay? Is that clear? Right. So this is called alpha weighted binary classification because now there is an alpha factor in the distribution. So we define the cost of misprediction. Misprediction means the mistake that we do as alpha, which is greater than 1 when the actual label is positive and 1 if the actual label is negative. Right. Now, we want to use what we learned about binary classification. So how many binary classification models we studied so far? Decision trees, KNN, and perceptron. Okay? And of course we will inshallah study more. So we want to use the binary classification models for this problem, the ones that we used to use as they are. Okay? So given a good binary classifier, how can we solve the problem that we have in hand now? So that's the question that we will inshallah answer. So the solution is, we will not change the algorithm itself. The binary classifiers that we studied, we will use them as they are. But as they are, they treat every example equally, right? They have the original error function, which is just treating all mistakes equally. How can we convert this without changing to solve our problem, to implement the new error function. The solution is really simple. We will train a binary classifier, whatever binary classifier that you like, on what we call an induced distribution. Induced distribution means it's something that is processed from the original. It's a new version of the original. The original distribution is unbalanced. It's completely unbalanced, right? So if I want to change the distribution so that I can use the existing binary classification, how should be the new distribution? Balanced. Very good. Straightforward, right? So the solution here is to reduce the problem from alpha weighted binary classification into general binary classification by making or by creating an induced distribution, new distribution from the original one. The original one is completely unbalanced. I will create a new distribution that is balanced and then pass it to the classifier as we usually do. Right. Now we have unbalanced distribution, right? How can I convert it now? So this is the question. How can I convert this completely skewed or unbalanced distribution into a balanced distribution? Any ideas? Scale it. What do you mean by scale it here? How can we scale a distribution? We have samples, right? We already have examples. We have, let's say that we have training data. Okay? This training data, let's say 100 examples. 90 of them are negative and 10 are positive. This is 1 to 9, right? Ratio, right? How can we make this ratio 1 to 1? That's the question. How can we make this ratio 1 to 1? Any ideas? Yes. Take 10 from the 90 and ignore the others. And keep the 10 from the positive side, right? Okay, if we do that, then yes, we will have 10 versus 10, which is completely balanced, right? This is called subsampling. This is exactly the idea here. This is called subsampling. So it's also called undersampling, by the way. Either subsampling or undersampling, they are the same. So we will undersample the negative class. So all positive all positive examples will be the same, will be retained, will be kept, will not touch them. But the negative samples from every alpha examples will take just one. It's like we divide by alpha. Alpha in our example was 9, right? So every nine examples would just take one. So the size at the end of the negative side will be just 1 instead of 9. And will be exactly like the positive class, right? Now, this is called an induced distribution. We started by a real distribution, and then from it, we did some processing to it, and we came up with this new induced distribution. Now, we will pass this distribution, this new distribution, to any binary classifier, the binary classifier that we like. And in this case, it will, of course, it doesn't see the original distribution, it sees the induced distribution. And will not have this original problem because now it will treat all the examples equally, which means it will treat the positive class equally to the negative class. Right? Is that clear? Any questions? Yes. Copies, you mean duplicates? This is very trivial. We should not have duplicates. We assume that we don't have duplicates in the data. If there are, of course, they should not be counted أصلاً من الdistribution. Okay. Yes.
I didn't understand. You said there's 10 examples to begin with, and then we take 10 examples from the induced class.
No. I said, okay, so here's the numbers that I mentioned. So let's say that we have two classes, right? We have positive and we have negative. originally we had 10 from the positive and 90 from negative. We will keep these the same, we will not touch them. And from this 90, we will sample how many? 1 every 9. So we will get 10. Alpha here is 90 over 10, right? Which is 9. Okay, is that clear now? Okay. Any other questions? So the solution here is clear. It's very simple, right? But it is an elegant idea. Type. What are the pros and cons? What are the advantages and disadvantages? Let's talk about advantages. Type. Raise your hand, please, if you have an answer. Yes. Okay, so now we have balanced data. Okay, so we can use any binary classifier, right? I mean, without changing. Good. What else? How about time? The time is reduced, right? Yes, time is reduced. Which time? Training. Training time is reduced, right? Why is that? Because now instead of 100 we have 20, right? In that example. So the training set is much smaller. Of course, the training in general will be faster. Unless we are talking about KNN, for example, because there is no training, but that's a special case. Okay, in general, training will be faster. Anything else good for that? But what's bad about this? Yes. Yes, so in general, let me generalize this. We are discarding labeled data, which is in machine learning precious. That's the treasure that we have. Okay, so we are just discarding them. We're just removing them, not using them. This is a big loss. Okay, so that's a big disadvantage. We should not, unless we have to, we should try to avoid this. So that's a big disadvantage. What else?
Won't the small
Yes.
sets be a problem?
Yes, so training on a small set might not produce a good classifier, right? So there is also a risk of having a not well-performing classifier because now the training set is much reduced. Okay, so that's another con. Type. The other idea is the opposite. Okay, instead of undersampling, we'll do oversampling. We undersampled here the negative class, right? In oversampling, we will oversample the positive class. So in oversampling, we will oversample the positive class. If we started with the same 10 to 90, then we will copy each one of the positive examples. How many times? 9 times, which is alpha, right? So we'll copy each one of these 9 times, so we'll have 90. Now we'll have 90. Of course, in this case, we will not touch the negative examples. So we'll have 90, 90, which is 50, 50, balance it, pass it to the binary classifier. Okay, so that's the other idea. So the first idea, subsampling, undersampling from the negative class. This idea is the opposite. We oversample from the positive class. And of course, pass now the solution to the binary classification. Same question, pros and cons. Yes? Sufficient data, or in other words, we didn't discard any data. Okay, so we used then the entire labeled set that we have. Okay, so that's something good, right? You don't see it good. No, we're not taking, yeah, we are keeping the negative. We didn't touch the negative, and we just copied from the positive. So we didn't ignore any of the labeled data. Anything else? About the size of the data now? Size is bigger, right? So we would expect the performance of this model to be better than the other model. Now to the cons. Why not? Now, the idea here is that we want to emphasize the importance of every positive example, right? So let's say, and let's take Perceptron as an example. Perceptron goes through the examples, right, and try to predict the label for each example. If it's mispredicted it will update, right, and then pass on it again. Here we are giving the model more chances to correctly predict the positive examples than the negative examples. So we are pushing the model to learn more about the positive example, although we have very small original sample from the positive class. Okay, so that's the idea, and this is the good side of it. Okay, that we are emphasizing more every single example from the positive class because it's actually important. And imagine, usually it's not, by the way, 10 to 90. It's much severe than that. It's sometimes 1 to 1,000 or 1 to 10,000 or 1 to million. Okay, so every single positive example is very important, and we need to make sure that the model really learns from it. Okay, type any other positive, not positive, negative point? Yes. Yes, training time will be more, of course, right? Because the training size increased, so the training time is more. So that's the other side. Type. Although we said the training might be affected, in some cases we don't even need to duplicate the examples, so the actual training will not be affected at all. And I can show you, okay, can discuss now one of the example models that we already studied, which is KNN. Let's think about KNN. How can we modify the KNN algorithm to do this without even copying the examples? We don't need to even copy every positive example. Can you think of how we can just make very slight modification to the way that KNN works so that it can consider the copies without actually copying the examples? The question is, how can we modify KNN so that it will consider alpha copies from the positive examples without actually copying the examples? Without actually computing the distance to the positive example 9 times if alpha is 9. Type in, let me be clear. We don't need to change k actually. Okay, whatever k is that we are using, we don't need to change it, right? We just need to treat every example, every positive example in particular, differently. I think I said it. Yes.
For example, if we have a point that we want to find, and then 2 negative and 1 positive around it, we would give more weight to the positives instead of counting 1.
Okay. That's what Mariam said earlier, but what is that weight? Alpha. Yes, alpha. That's the weight. So it's like counting the vote from the positive example alpha times. That's it. And just multiply whenever we have a vote from a positive. Whenever the positive example is among the neighbors, the k nearest neighbors, then its vote will be counted alpha instead of 1. Exactly. That's it. We don't need to make copies of the example. We don't need to change anything except this. Okay? Is that clear now? You want to say anything else? Okay. Type. How about decision trees and Perceptron? Can we change them in some way? I will leave that to you. Think about it. Okay. Type. If you remember last time, we mentioned that the concept that we will learn, the machine learning concept that we will learn in this session is called reduction. And this is actually what we did. We reduced the alpha weighted classification problem into binary classification problem by just changing the distribution. We call this reduction. Okay? Reduction in general is like conversion. We are converting a bigger problem into smaller problem. Okay? Or we are solving the bigger problem by a solution to the smaller problem. Okay, that's what we mean by reduction. So here we are reusing simple and efficient algorithms, which are the binary classification algorithms, to perform more complex tasks, like the task we are doing, which is the dealing with imbalanced data. Type. What is the relation between the error of the binary classifier on the new distribution and the error on the classifier on the original distribution? If the theory here says that if the binary classifier that is used in subsampling, for example, if the binary classifier used with the new distribution, let's say that it achieved an error rate of epsilon. That's on the new distribution, the balanced distribution. Then the error rate of the classifier when we use it on the original distribution, the alpha weighted classifier, when we use it on the original distribution, will be alpha times epsilon. So the error will be bigger than just the error on the original distribution. And that's because every single positive example now is like alpha times the negative example, whether with subsampling or oversampling, and thus the error in that is much more severe. Okay, so the error rate here is more. And the same on oversampling, same for oversampling. So whether we do subsampling or oversampling, if the binary classifier on the new distribution has an error rate of epsilon, then the actual error rate is alpha times epsilon when we try the classifier on the original distribution. Now, I have two questions. One is not on the slide and the other will be on the slide. The first one, why should we care about the original distribution if we already converted to the new distribution and we used it? Why should we care about the original distribution? Yes. Yes, because that's the real life distribution, right? Now we are building that classifier to be used in reality, not just to be trained in an experiment, right? So when it is used in reality, this will be the error rate. Okay, so this is the first one. The second one, if this theory says either subsampling or oversampling, we will have an error rate of alpha epsilon, where epsilon is the error rate of the binary classifier. Does that mean that both methods have the same error rate? Why not? Now you know the answer. The answer is no. Okay, no, it's not the same error. Although the theory seems to say that they have the same error, right? If it's epsilon, then it would be alpha epsilon for both. Is there a contradiction here? Yes.
Because the data for undersampling is different from the data for oversampling. So definitely
Thus, when we train a binary classifier on this, its error rate will be different from the binary classifier on the other one. So epsilon here is different when we talk about oversampling than undersampling. So which one should be better, you think? Oversampling, right? Because it has more data. Okay, so the error rate, of course, should be a bit more expected to be smaller in the case of oversampling. Okay. Any question about this? Now we'll switch to multi-class classification. Any question about imbalanced data? So you know now two ways with pros and cons of each to solve the problem that you might face at any time that you have an imbalanced distribution among your classes. Any questions about this? Right, let's switch to multi-class classification. I think you heard about multi-class classification before, right? So we have multiple classes. Is that a real thing? In reality, we have multi-class classification problems like what? Yeah, so you see the symptoms, and then you might have many possible diseases. Okay, so that's another one. Someone, yes. Type of, and you like birds, seems like you like these things. Okay, type of trees and type of birds. Okay, We mentioned also earlier something like this, the reviews, when you want to say positive or negative, but that's binary, right? Sometimes we also want to detect the ones that are neutral. Sometimes we put a review that is not completely positive and not completely negative, so that should be a neutral. Or the type of a movie, like action movie, comic, things like that. What could be the third one? Fantasy? I don't know what you mean by fantasy. Okay. Anyway. Okay. So political, sports, health, things like that. Okay. And if we're talking about maybe news articles, like when we type a query on Google, sometimes, for example, if I wrote 1,000 Qatari riyals $2, it will know that this is, you want to convert, to do conversion, right? If I typed time in Cairo now, it will show me the time, right? It will not, it will give me some results, but it will show me also time. And the other one, it will show me the conversion, okay? So Google does query, what we call query classification, to know the type of the query, and based on that, it might serve the results in a different way, okay? Some queries might be about images, so it will show you images even at the top of the links, and so on. So that's anyway. I think I convinced you that there are many real-world problems. Now, with the models that we learned, decision trees or KNN or perceptron, how can we perform multi-class classification? I think we discussed that many times over the lecture. So quickly, decision trees. How can we use decision trees to do multi-class classification?
You will search for, instead of two answers that are with three, and then order the tree with the more correlated to the label.
Yeah, so at every time when we make a decision about the feature, we get the distribution, right, of the labels. So regardless of how many classes we have, we can get the distribution, we get the majority, or we can compute the scoring function. So it's naturally it is multi-class classification. It's not specific to binary. Okay? Same with KNN. So KNN, we get the votes from different classes. They don't have to be positive and negative. Maybe the examples that we saw are always positive and negative. That's because they are easier to do it that way. But there is no restriction from KNN itself that we have to deal with two classes only, right? It can be many classes. How about perceptron? Think about it in 2 dimensions. If you had 3 classes, can you use a line to separate the 3?
No.
Type. Anyway, perceptron can do multi-class classification? No, because the inductive bias, the basic assumption is that the data can be separated by hyperplane. So the model, the decision boundary is a hyperplane. Hyperplane cannot, to my knowledge, cannot separate more than 2 classes. Yes.
Giving the geometry of the perceptron, I'm speaking about its theory. We are multiplying each example with its way of doing the bias, and then we are making the result into some kind of activation function.
Yes.
Our activation function so far only classified for 1 or -1.
Yes.
Maybe because this is the طبيعة activation function. If we change the activation function.
But now you are changing the perceptron completely. Yeah, you are talking about something that, yes, now if I used, and we will see that in neural networks, if I change the activation function to be nonlinear, خلاص, then I can. I can with some of them, I can do, of course, multi-class classification easy. But I'm talking about perceptron as it is, okay, without changing it. Okay, so perceptron naturally will not be able to do multi-class classification. Type. Let's just get to these 2 slides, and then we will, inshallah, finish quickly. So multi-class classification. This is the definition. If you saw the definition here, the only difference between this and the binary class classification, the binary classification, is this key. Trying to get that key. So the label now is not positive or negative. It is one from K classes. Okay, so that's the only difference. How many classes in practice we use? Usually we have few classes, like 4, 5, maybe 10. In some cases we might have even something like 80, 90, but usually it's less than 100. If the problem has more than 100 classes, then probably you need to restructure the problem in a different way. So you need to think about it maybe differently.